So, in the last lecture we stopped at some of the configurations of a dye laser. We will go on with that. I still have not spoken about the most important part of that resonator of a dye cell is the tuning element. So, that is what we will speak about in this lecture. Okay. So, what is the tuning element? You have that wide spectrum. So, one of the tuning element or the most popular one is a grating. Okay. So, here I have the grating. The most popular one is this grating. You can have elements which are Fabry-Perot, which is a interference based selection element, and or you could have mirrors which are coated specifically for a particular wavelength. But the grating is the most useful element, I should say, and then gratings are have been used even in monochromators for ages, and there have been lots of improvements in the kinds of gratings that are being used. Okay. And it is a old one and well used and useful, no doubt about it. So, we will talk about the grating in a little bit more of detail, because it can be used anywhere. It is of course used in the dye laser resonator. So, what you can see here is the dye cell, as I have shown before, with the dye, and there is a flow system going on, and here is the pump beam, pumping system of the dye. So, there is a pumping system and there is a flow system attached to it. The flow systems I have not shown here. Here the pumping system is shown here, and the two mirrors of the resonator, one is M1 here and one is M2 here. And then you have this grating element which is within the resonator. The idea of having the grating element within the resonator and not externally is because you can choose that particular wavelength, and you can have stimulated emission at that particular wavelength only, and so the intensity really grows. But suppose you had that grating outside your resonator, okay, you could have had a grating outside the resonator too, to choose the particular wavelength that you require. Okay. It could have been somewhere here at the end of this, a grating here, you choose the wavelength, this is coming out with a whole set of frequencies, and you have a grating and you choose the particular wavelength that you require. So, here again with the mirrors, and here again with the mirrors, and then you put the grating. But the disadvantage there is you are losing out on energy once again if you keep that element outside your resonator. So, you would like to keep it inside the resonator, you make the selection there and you make the stimulated emission occur at that particular frequency or at that particular wavelength. Okay. And you have a very high intense laser beam, as laser beams are. So, that is the whole idea of keeping the grating. Now, how these gratings will have to be placed, sometimes even two gratings are used, how these have to be placed depends on the grating rulings, depends on the type of grating, depend on the understanding of the grating element itself. You would have studied it in optics even before, but I think at this point I should reiterate what you have studied before. Oh, it is a very common element. Okay. So, let us just go through some of the properties of a grating, and then you will understand very well why it is required for your dye laser and why it should be placed within the resonator itself. Okay. So, a grating, as you know, has many grooves that illuminates coherently, can be regarded as small coherent sources each of them diffracting the light onto the small grooves of with about one wavelength, okay, lambda, into a large range of angles. Okay. So, this is the grating. I have just shown a blown up picture of that. So, these are the grooves, and this is your input light, and this is your diffracted light. I am talking about a reflection grating, but you do get transmission gratings too, and the treatment of the theory is just about the same for both. Okay. And this is the distance between the grooves. So, alpha is the incident angle of the incident wavelength with the normal to the grating. Now, this is what has to be understood, with the normal to the grating. So, you see this red line, this is the normal to the grating. You see it is normal to the bottom part of that grating, and this line is also the normal to the grating. So, it is to the bottom part of the thing. Okay. So, this is what a grating looks like in a blown up proportion, and the famous grating equation I have written down here, d sin alpha plus minus sin beta is equal to m lambda. M is an integer, lambda is the wavelength you are dealing with in this grating, and d is this distance between two grooves. Okay. So, m is an integer, it can be 1, 2, 3, 4, 5, 6 like that, and this is a very famous grating equation, and as we go through the whole procedure you will realize why this is such an important equation and how did it come about. How did such a equation come about? When we derive all the properties of the grating on the light, then you will realize why this has come about. For the moment, just assume this is an important grating equation. Okay. So, I have described the normal to the grating. Now, you have a look at this picture. This is also an expanded view of the grating, but here this is normal to the groove, and this groove also has a particular shape. Why does it have such a particular shape? You can get grating the action, the diffracted action from a grating even if you had grooves like this. Okay. So, they need not have had that angle, but that angle is a very important angle, and the moment you have that angle, if you had a grating like this, you would be describing only the grating normal. You will not think about the groove normal, because it is at a slant like this, because the grooves are at a slant like this, you need to describe a groove normal. Okay. So, here I am just talking about just one groove, and it has this slanted structure. So, I have an incident beam and it will be reflected here, normal reflection. Okay. And if it is part of the whole grating system, you might get reflections of the same wavelength. You have the single wavelength you get here, there is no dispersion here at all, it is just plain reflection, and r is the angle of reflection and I is the angle of incidence. Okay. Okay, this is if I consider only one groove. Now, I am talking about, now you see in this picture, I have drawn the grating normal as well as the groove normal. Okay. The grating normal is perpendicular to the base here, while the groove normal is perpendicular to this slanted surface, and there is an angle between them which you can understand, which is given by theta, and it is also the angle of the slant of this groove is theta. You can easily see this comes here. So, I is the angle of incidence, okay, that is between this and this, but here alpha that I have shown, alpha is always the angle of incidence with respect to the groove, with respect to the grating normal, and beta is always the diffraction angle, angle of diffraction related to the grating normal. Okay. And here I have put plus minus sign, plus and minus sign here, because it depends on did the diffraction happen on this side of the normal, or quite often the diffraction can happen on this side of the normal also to the grating normal. Okay. If it happens on this side, the direction where this circular bit is going, then you have to put in a plus sign. If it is on this side, then you have to put a negative sign. That is why plus and minus is put there. Depends on which side the grating has gone. Sorry, here. Okay, so what you have to just know the difference between the groove normal and the grating normal, and this angle is called the Blaze angle. Okay. It is called the Blaze angle. That means quite often, suppose you were to buy a grating for your systems in the laboratory, you have to give certain specifications. Okay. Or if you want to make it yourself, you have to make it with these specifications. These means you have to give the number of lines that are there on your grating, and you have to give this Blaze angle. Or you have to identify and say, I want a grating with a blaze in a particular wavelength. So quite often this Blaze angle, which you refer to with respect to a wavelength. So this part can be coated in such a way that it reflects the particular wavelength in an optimal way. Okay. Let us see how that optimal way works. Okay. The reflectivity R beta 0, beta theta, beta is the diffracted angle and theta is between the two groove normals, okay, of a grating, depends on the diffraction angle beta and on the Blaze angle theta. So theta is called the Blaze angle. The Blaze angle is the angle between the groove normal and the grating normal. Okay. If the diffraction angle beta coincides with the angle R of the specular reflection from the groove surface, then R beta theta, R which is a function of beta and theta, reaches its optimum value of R0, which depends on the groove coating. Okay. Now, okay, I have put in all these words. What it actually means is, see here I will just get a normal reflection. If this theta and beta coincide, okay, so my diffraction is such, so here these two lines they are the diffracted rays. This is the incident ray and this is a reflected ray, and these two are the diffracted rays. Suppose these two diffracted rays coincide with this, then you will get the optimum, or you will get the optimum intensity. Okay. So it is not always the case, because you know this diffracted rays depend on the normal here, the groove normal, but suppose, and diffraction depends on all the number of grooves. Okay. So, but if they coincide, then you will get the best reflectivity. So, you will really look for that. Okay. So, now the diffraction angle will depend on the wavelength, which you will realize even as we go through the explanation. Okay. So, it will depend on that. So, you have this from the diagram, from the previous diagram, it is evident that I is equal to alpha minus theta and r is equal to theta plus beta. Now, when I is equal to r, that means that this is the usual rule of reflection. Okay. Angle of incidence is equal to angle of reflection, okay, for specular refraction. Then alpha minus theta is equal to theta plus beta. So, theta, this angle, the Blaise angle, is given by alpha minus beta by 2. So, you can calculate the Blaise angle for a particular wavelength, and you can specify to the makers of your grating. Okay. The condition for optimum Blaise angle, this is the condition for optimum Blaise angle. Okay. So, generally you will tell your supplier that I want a grating with the number of rulings. Okay. Number of rulings means these. So, these are the rulings. Okay. So, you have to give the number of rulings. So, it is given as say 600 lines per mm, or it could be 1800 lines per mm. Okay. So, you have to give, this is one parameter that you have to give them, and you have to give the parameter of that Blaise. Generally, you give that parameter of the Blaise by giving him a value of lambda that you will be dealing with, the kind of lambda that you will be diffracting from such a grating. Okay. That will give him the Blaise angle, or you can specify the Blaise angle itself. Okay. Because, and it is important you can understand, is because you are getting the best intensity when it is blazed for a particular wavelength range. Suppose you had a grating only like this, which are just like this, then it is difficult to get a good intensity. You will get diffracted light out of this, but with a Blaise angle you get a much more better intensity. Okay. So, let's study the grating equation a little bit more in detail. Okay. Okay, let the grating consists of n grooves and each contributing a reflected wave. The total reflected electric field is the sum of the field from each groove. Okay. This is similar to a interference pattern. Okay. So, you are getting a small wavelet, say from this groove you are getting a small wavelet, from this groove you are getting another wavelet, from this groove you are getting another wavelet. And all these wavelets are coherent because your incident light itself is coherent. Okay. But then all of them will superpose with each other, and that will give rise to an interference pattern. What kind of interference pattern is that? That is what we want to know from a grating, and how it will help me to get my laser to tune. Okay. So, here I have E total, that is total. This is some of the derivations which I have done before also in previous lectures. It is similar to that. I have this electric field, E I have given as the electric field. As you know, the total electric field out of all these small electric fields from the grooves will be proportional to Z, because Z is the physical direction, and T and the time also, which is given by the sum of all those small waves. Suppose there are n, because there are n grooves, so there will be n wavelets. So, it is proportional to E dash is some amplitude, and then e to the power minus I kz minus omega t plus phi. Okay, this is like a standard wave equation of that field. Okay. So, what I have to do is I have to know this phi n, and z is the position of the nth groove. Okay. So, obviously, it will be proportional to that physically at which point, and z is equal to nd. So, d is this, n times that d will give you the position at the nth groove, okay. And phi n is the phase introduced by the grating at that particular groove, the nth groove. So, this n is equal to 0 to n minus 1 is these are the groove. You just identified the groove as 1, 2, 3, 4, 5, 6. So, these are integers. So, this is like a standard equation. Then the phase shift is proportional to the path difference delta, okay, in this diagram. So, delta is equal to d sine alpha minus sine beta, okay. This is the path difference. Now, this is the most important. See, it is looking like a little bit like the grating equation, okay. So, this is the path difference. Here I have the input beam, this is also my input beam, and this is my diffracted beam, this is my diffracted beam. The green ones are the input beams, and the purple ones are the diffracted beams. And alpha is the input angle, incident angle, and beta is the diffracted angle. So, if you really see this part, and if you really see this part, and you make a perpendicular here, so the path difference between these two rays, these two are say rays separated by this much distance, will be this part, you know, the dark part of the green that I have shown here, okay. And the path difference between this diffracted ray, which is given by this perpendicular, if you draw between these two, then you will have this part, which is a darker purple part, which gives you the path difference between these two rays. So, you have a path difference between the incident ray itself, and you have a path difference of the diffracted ray itself, okay. So, you have to add these two difference in path to give you the phase difference between two consecutive wavelets that are coming from two consecutive grooves. So, this part is its simple geometry from here is d sine beta, and this part is d sine alpha, okay, this part. So, you have to add these two. So, that is what I have done here, sine alpha minus sine beta. This is just giving me the path difference. The phase difference will be k delta, that you already know. K is the wave vector. Wave vector is given by 2 pi by lambda, same wave vector which we have discussed before, okay. So, k into delta gives you the phase difference. This is the path difference and this is the phase difference. So, the phase difference is k d sine alpha minus sine beta is equal to 2 pi by lambda, that means k, I have substituted for k, d sine alpha minus sine beta. Okay. This is the phase difference, that is brought about from one groove to the next. Okay. Now, like that there will be n number of grooves. The next groove will again have a path difference with respect to the first groove. The third groove will have a path difference with respect to the first groove. So, we have got to add up all those path differences to get the actual phase difference. Here phi is giving you the phase difference. So, here I can write this equation. I will just separate out the time part and the space part. We are not really bothered about the time part now, okay, omega t, which gives you as the wave is travelling what is happening to it in time, but we are more bothered about the space part. Okay. So, I will just separate it out. So, I have put that e dash e to the power minus I omega t outside, and I have kept the space part only inside, and I have substituted for that phi n. So, it is I n n is varying from 0 to n minus 1, k d sine alpha minus sine beta. Okay, I have kept the sign minus here because my diffracted beam is on this side of the groove normal. Okay, this is a groove normal here, and d is the distance between the grooves. This is a groove normal, the red dashed line. So, it is on this side of the groove normal. So, I keep that negative sign here. If the diffracted angle were on this side, it would be positive, and the procedure of doing this mathematical derivation would have been just the same. Okay. So, now I have separated out the time part and the space part. Okay. So, here it is. So, that is why, because I have separated out, and here I just take the space part of it. So, E total z, I have put a proportionality sign here, is equal to e to the power I n phi. Superposition of the fields from the nth groove, from the n groove, results in the formation of total field E total, which is this total. Okay. Now, how do I add all these things? Now, this is a bit of algebra. Okay. So, this part is a geometric progression, something like that, and the identity is given by this. So, I just substitute that E total z, because 1 minus e to the power minus I n phi, and this is proportional to this, okay, and into this. Here what I have done is, I have just taken out e to the power minus I n phi by 2. This I have just taken out common, and I have written this in this way. I have done that because this I can write as sine n phi by 2 and sine phi by 2. Okay. So, these two equations are similar. So, I keep putting this proportionality sign because I have removed the time part of it, and we are interested only in this. Now, what does this look like to you? This is the field, the electric field, because we started with that field. But if I want the intensity, I have to take the square of this or complex conjugate of this. Okay. So, I have written the intensity as I0 sine square n phi by 2. Okay. And here I0 sine square phi by 2. Okay. So, does not this look familiar? Okay. So, this should be familiar to you, this kind of an equation, and it is a very famous equation. So, this shows that I will get principal maxima occurring for phi is equal to 2 m pi, m is that integer. So, 2 pi, 0, 2 pi, 4 pi, like that. Yeah. Those will give me a maximum, this will become a maximum. And you see here I am putting phi is equal to 2 pi by lambda d sine alpha minus psi beta is equal to twice m pi. So, I am getting m lambda is equal to d sine alpha minus sine beta from here, and this looks very familiar. It is the main grating equation. And the pattern that you will see looks something like this. Okay. So, what you have is, you just note this equation well. What you have is that grating will decompose a beam of non-monochromatic light into a spectral orders. You see at different incident angle maybe is the same. The diffracted angle and the lambda, they are related to each other depending on the order. So, depending on the order, you will get different angles at which you get that order, and you will get a different wavelength. So, you are doing a tuning of your wavelength. So, if I go back to this, See here. So, the grating is bringing about a tuning. You have so many wavelengths here. So many wavelengths are possible, but you are choosing only one just with this element, grating element. So, the grating element is one of the greatest tuning elements possible. Okay. So, here I have this. This is how I have achieved tuning. Okay. And this is what the spectroscopist is looking for. He wants that tuning. Next time I will go on to explain to you some of the uses of this tuning. Okay. And of course, I will describe even Raman spectroscopy, which wouldn't have become so popular if the intensity of the lasing light were not used in Raman spectroscopy. So, I hope you have understood the tuning part of the laser of any lasing system, how it helps a spectroscopist.